smart, optimal, and risk-adjusted electric vehicle scheduling in microgrid and active distribution system. So let's see what is it all about. Actually, Merlin?
Yes, sir.
I cannot go. Okay. Now it's possible. It's not about to move the slide. Okay. So the figure which I am showing here is the microgrid standard architecture as per IEEE 1547.4 standards. I'll just go through the basic framework of EV scheduling and the economics and technology of microgrid with V2G activities. At least some of you may seem these things obvious, but for those who don't have a background, I'll just go through it for 1 or 2 slides and then we'll move on to the advanced level. So here you can see there is a feeder substation. Let me change my 1 minute. Okay. Are you able to see the cursor? Yeah. Okay. So you can see a feeder substation here and a distribution system which is active. So active in the sense we have distributed generation here, then plug-in electric vehicles are there, then distributed storage is there, then apartment loads are there, residential loads are there, many other loads are there. So basically we have a subsystem also. You can see here with this one, the bottom one is a subsystem having a separate isolating switch, which is known as the commercial switch. And to isolate the whole system, we have a centralized switch, which is a utility microgrid switch. So from the utility side, we can even completely isolate or island this system, or we can have a local islanding process also, an activity of local islanding also by using the commercial switch. So now the framework is that any scheduling process should be planned before or prior to the actual time horizon in which the actual transaction happens. So actual transaction in the sense, it can be the dispatch of distributed generators, then the dispatch of distributed storage or the charging of distributed storage. So here the output power can be positive or negative for distributed storage. Similarly for plug-in EVs also the output can be negative or positive power, active power. I'm mentioning about active power now. Then the loads. So of course, if demand response is there, then the flexibility of load should be mentioned prior to the actual real-time horizon. So based on this plan, some third party, any third party can be there. It can be the distribution system operator itself who operates and sometimes owns the microgrid also. Sometimes he will just act as an aggregator who purchases power from the sources and sell it to the power sinks. That means sell it to the end consumers. So let's take this scenario in which the third party purchases power from the distributed generation or the storage or the plug-in electric vehicles, and he sells this power to the loads or end consumers, and he has the right to pump the power to the grid also. So he's as of now he is responsible for both technical and economic activities in the microgrid. Now what's the need of scheduling? So prior to the real-time horizon itself, we'll have an idea about the forecast of distributed generation. We know that mostly distributed sources are renewable energy sources. So we have the forecasted values only regarding about the solar irradiance or the wind velocity. We'll have some forecast. Then we will have load forecast also. Now coming to the plug-in electric vehicles, we have an idea of how many electric vehicles are available, are supposed to be available in the parking lots. Each parking lot. It's a pooled kind of system, but n number of electric vehicles are there in one parking lot itself, especially if it's an apartment or so. Then we have a pooled parking. So the capacity of that parking lot with respect to discharging and charging is high. So based on this, it should be communicated to the third party, whether it's an aggregator or the distribution system operator. It should be communicated to the aggregator prior to the real-time horizon, and he will work out some dispatch plan. And this dispatch plan is basically this process of planning the dispatch is known as the scheduling. Now, what's the challenge of scheduling? Because we completely depend on the forecast now, but in the actual time horizon, it may deviate from the forecast. So the actual output may be different according to the real-time solar radiance from the PV modules, then the actual wind velocity, the real-time wind velocity, and the real-time state of charge available in the EV batteries. So this is a bit different from the scheduled dispatch. So the risk of deviation from the scheduled must be taken care of while scheduling itself. That is what is meant by the risk adjustment, the term risk adjustment. In the title also you might have seen risk adjusted scheduling. So that is what is meant by risk adjustment. Now another term is there which is smart. What is smart? Suppose in the parking lot there is a login and logout system. Whenever a car comes in, it logs in and it's marked there. It's digitally marked there, and when it goes out, it logs out. So if this information is stored and saved in a cloud, and if it can be communicated to the aggregator, and if the whole process is automated, then we have a smart parking lot there, right? So similarly, if the distributed generation also at each house, you know that we have smart meters. So nowadays smart meters also have the capability of communicating to the cloud, and in a centralized platform, the controller, the microgrid central controller or the distribution system operator or the aggregator can see the status. So with respect to that also, it's smart. So in general, the system is becoming smarter. That's what. Now, another term you have seen here is optimal. See, what's the objective of scheduling? The objective can be economic, right? It can be a minimum cost objective, or it can be a maximum profit objective, or it can be technical objectives also. Suppose we have, based on the dispatch, you know that the nodal voltages are deviated from the nominal values. So if you are too much taking care of the values, then you can even keep the objective or design the objective based on voltage deviation, the voltage deviation minimization. That means actual voltage minus the reference voltage, or vice versa. So this could be minimized. That can be another objective. Or some other operator can give preference for power loss in the system. So it can be power loss minimization also sometimes. Now it can be environmental objective also, because if you are depending more on renewable energy sources, the carbon emission is less. So if you are keeping the objective as emission cost, and if you're trying to minimize it, then it's environmental objective. So based on all these things, we are working on the microgrid plan accordingly. Risk adjustment is done. Objective is kept. Objective is designed depending on these things. And optimization is done taking care of these uncertainties. What are the uncertainties? Renewable energy itself is uncertain, right? That is the cause of deviation from the schedule. One of the causes of deviation from the schedule. Then the distributed storages, the uncertainties in state of charge. Then for plug-in electric vehicles, there are uncertainties in the trips of the vehicle, right? So based on the trips of the vehicle, SOC can change, or the number of electric vehicles which is expected to be in the parking lot itself can change. So the pooled power injected from that particular parking lot node will change. So if all these uncertainties are properly modeled using some approach, and if we are able to work out a realistic schedule, then it will be good. Now, what is the impact of having an uncertain schedule or an unrealistic schedule? That we'll see in the coming slides. So this is what is the content of this presentation. the need for scheduling, then the framework of scheduling, then the challenges with uncertainties, then how to solve this problem, how to model the uncertainties properly. Then we'll have 1 or 2 case studies, then conclusion and prospective research areas. Now, let's see. Here, V2G and G2V functionalities. What are the potential functionalities of vehicle to grid and grid to vehicle activities? It can be used as normal battery energy storage, right? From the home itself, it can act as a home charging unit or home discharging unit. If it is connected to the grid, it's a grid charging unit and grid discharging unit. Then another possibility is, see, 4 more possibilities are given here: reliability islanding, peak shaving, voltage regulation, and frequency regulation service. We will move one by one. We'll go one by one. So first we will see what is frequency regulation service from the EV side. See. Okay. Now, suppose the EV battery is able to give momentary power supply by discharging to the grid. Then momentary in the sense very short term. So in a short term period, it can support frequency, or it can regulate frequency if used in a pool. Because if a considerable section, a dominant section of society is using EVs, then from more of the parking lots, this particular frequency support can be provided. So that is kind of ancillary service. Ancillary service in the sense it's a supplementary service. Other than the normal energy transactions, a supplementary service can be voltage regulation, frequency regulation, or islanding support, or whatever. So for these things, the consumer is paid. Consumer earns some revenue based on these services. So we'll see how he earns revenue based on these services. Now, the annual revenue of frequency regulation participation, suppose you see this equation 1, R equals PR frequency into P megawatts into A, where PR frequency is the frequency regulation charge or the frequency regulation price, which is expressed in dollars per megawatt hour. This is multiplied with the capacity of the battery, which is committed for frequency regulation. So this is dollars per megawatt hour into megawatt will give you dollars per hour. And if A is in hours, then it's dollars per hour into hour, which is in dollars. So the revenue is in dollars. So A is the time duration in which the battery, the EV battery, is used for frequency regulation service. And this is the capacity that is committed for, capacity in terms of power that is committed for frequency regulation service. And this is the regulation charge, the frequency regulation charge. And this is set by the policy makers or the utility itself. There is no role for the end consumer for that. So wherever there is a variation in this price, accordingly the earnings may vary. So now you see, let us assume that a Nissan Leaf owner in the PJM interconnection is the largest electricity grid in the world, which includes it's operating roughly from Chicago to New Jersey. PJM means Pennsylvania, New Jersey, and Maryland. So this is one of the most it's a case study for ISO considerations, ISO activities. We use this particular interconnection system. So suppose we assume that a Nissan Leaf owner in the PJM interconnection can participate in frequency regulation using their home charger. Assume use of level 2 charger at home. Let us assume that the capacity of this Nissan Leaf owner is 10 kilowatts or 0.01 megawatts. So capacity of this Nissan Leaf owner, in the sense, this is not the total capacity. This is what he commits for frequency regulation service. So the charge for or the price for frequency regulation is given like this. It is charged for the capacity, which is communicated prior to the frequency regulation time horizon. Suppose I'm going to participate in frequency regulation service. If it is an hourly horizon, then if it is suppose from 3 p.m. to 4 p.m., then 1 day before or 1 month before itself, I'll commit. I'll say that for these many hours, I'll be committing my electric vehicles during this time period at this capacity. That is what is this capacity, 10 kilowatts. Now, next, acknowledging that there would be additional revenue, there was also a work charger. That means if he goes to office, if he is providing some V2G activity there also, he can earn more. But at present, we are not considering that here. We are only assuming that the V2G activity is happening only from home charging. Now, we assume that the EV is available to provide V2G services Saturday and Sunday. I mean, Saturday, keep it for 23 hours, and other days he is keeping it for 15 hours, adding up to about 6,300 hours per year, which means 72% of the time he is keeping it in the parking lot itself. This is not about one EV owner. Actually, it's a pooled system, but we are taking one EV owner into, I mean, for the sake of case study. Finally, the average price for frequency regulation in PJM was $34 per megawatt hour. So this PR frequency is $34 per megawatt hour. Now, what is P megawatts? Which is 0.01 megawatts. That is a committed capacity for frequency regulation. And what is the total number of hours? That is 6,300 hours per year. So thus we can calculate the annual revenue. So by this equation, we get the annual revenue for this hypothetical Nissan Leaf owner as $2,140. But the whole amount is not for the owner. A portion of this has to be given to the aggregator for facilitating this service. He is the owner of the infrastructure, or he is who acts as a third party, who takes the role of the third party. So a portion has to be given to the aggregator. Now, adding a V2G capable charger at work increases this annual revenue by about $600 per year. So if he participates in service from office also, he gets $600 more per year, which may be cost effective for the owner to invest in EVs, because we know that the upfront cost for EV is more when compared to gasoline based vehicles. But if he invests, such an avenue is there for earning, then people will be more encouraged towards investing on EVs. Thus, depending on the time frame, V2G revenues can add up to tens of thousands of dollars over the lifespan of the vehicle. For example, the 2018 Nissan Leaf costs a consumer in the USA as low as $22,490. This is the upfront cost for EV Nissan Leaf. This is in 2018. Of course, this is not for Nissan Leaf Plus. One more model is there. I think for Nissan Leaf, 42 kilowatt hour battery is used, and Nissan Leaf Plus, it's 60 kilowatt hour, around 60 kilowatt hour battery is used. So you note this point, because only 10 kilowatts is committed for frequency regulation. Even though the battery capacity is more, this is the only capacity which is committed for frequency regulation. Okay, so it's more practical in that sense. Now, in theory, it would take only 10.5 years for an owner to recapture that value in V2G revenues, not accounting for other benefits of EV ownership like reduced fuel costs. See, we are buying the car for travel, right? So the benefit of travel cannot be quantified in terms of money. That itself is a benefit. So in addition, you are getting these benefits. That is what he is looking for when he is investing on electric vehicle. So even though from operation side, he has fuel cost saving or maintenance saving. Of course, EV's maintenance cost is less when compared to gasoline based cars. So although these savings are there, in addition, he is getting this earning from V2G service also, frequency regulation service also. In addition, he can go for voltage regulation or other services, but this is just an example. Now, frequency regulation prices are variable over time and electricity grids. Now, the figure here shows for different interconnections. PJM is shown. This is one of the interconnections. Then New England is shown, New York ISO is shown, ERCOT ISO is shown, California ISO is shown. For all these interconnection grids, what is the range of regional net revenue for the EV owners? That is what is shown. So you can see here in PJM, it varies from $25,000 to some $52,000. This is the variation. Why this variation is there? Because prices vary over time. It's not same. The price which we have considered here, PR frequency, is the regulation price which is set by the utility or set by the system operator. That will change. Okay, so based on that, this will change. So the earnings is uncertain. We don't know. Now, as per plan, we may not get the earning also, because we assume that we don't have any trip on a particular day, and we assume that 15 hours the car will be there. But in reality, the car is not there. You have an urgent trip, you have taken it, and you have gone somewhere. So it's not possible, right? So there is uncertainty with the revenue also. And this portion of revenue is going to the aggregator. So in effect, aggregator's revenue is also uncertain. So these are, problems which have to be addressed in a stochastic approach, from a stochastic approach. It's not, everything is not deterministic. We have to go for stochastic approaches. We will see how stochastic models are made based on EV uncertainties or price uncertainties, and how to schedule it in a realistic manner as far as possible. Now, frequency regulation prices are variable over time. This we have already discussed. So figure shows the total revenues of a V2G owner providing frequency regulation over 16 years in the 5 electricity grid operators in USA, where the total revenues can range from just under $20,000 to over $45,000. These revenues depend on 3 factors. One is frequency regulation price, that is varying. Then power capacity. Capacity itself varies, because whatever he commits, he may not be able to provide at that particular time, because everything depends on practical planning. Then EV availability. The vehicle may not be available at the parking lot at a committed time period. So based on these revenues can vary. Frequency regulation price may vary significantly over time. Hence the relatively large error bars in the figure. This is one of the relatively large error bar, New York ISO. Error bars in figure. At the same time, power capacity and EV fleet availability can be increased, which both will increase the revenue potential. See, if you are planning properly, you can earn more. Because in some market frameworks, we have another guideline where if we are not able to acknowledge our commitment properly, that means we say that our EV will be available there, and if it's not actually available there, we may be penalized. Some frameworks are like that also. So if the planning is not proper, there is an expense coming in this particular activity. So based on that, the revenue will be cut. The total revenue, the net revenue will be reduced. The potential of V2G to reduce the cost of ownership over the lifespan of the vehicle could be quite enormous. Now, we have to convert the whole earnings, the total earnings of the lifetime of EV to the net present value, because we are investing on EV now itself. We are investing on the EV charger now itself. We are upgrading the EV charger for V2G activity. That also we are doing now itself, right? But our earnings are planned for 10 to 12 years or maybe 15 years according to the lifetime of the EV. So this has to be converted to the net present value. We can calculate that in our example above. The net present value of V2G to our hypothetical Nissan Leaf owner over 16 years would be, here it is assumed to be 16 years. The lifetime is assumed to be 16 years, would be $23,000, whereas undiscounted it would be $34,000. So by discounted cash flow, we assume that 23,000 if we is the the revenue that is earned by the Nissan Leaf owner as per the present value. So you can see that it actually exceeds the upfront cost. So it's a valuable proposition now to invest on EV if these activities are facilitated in your utility distribution network. Otherwise, of course, this V2G revenues will not be there. Only fuel cost saving and maintenance cost saving will be there. And of course, that subsidy you will get for using a non-fuel based vehicle. You will get some subsidy according to the policy of the regulator. Now, let's move on to the next slide. Okay. Now, so this was about frequency regulation service. That was one of the point in the V2G and GTV functionalities. Now we will move on to peak shaving, how peak shaving is done. So in the first figure, you can see that a 15 kilowatts local load is there. We have a parking lot here in which some n number of electric vehicles are available, but it's not switched to the system now. It's isolated from the system. But you can see here, because of this 15 kilowatts, the line which is connecting from the grid point to the local node is 150% overloaded because of the 10 kVA limit. It is 150% overloaded. So what can be a support from V2G side to mitigate this overload? Now you can see, you connect this parking lot, we are producing 6 kilowatts now. So out of this 15, 6 is locally fed and 9 only comes from the grid. Of course, losses are assumed to be 0 here. This is neglected, but you have to consider that. But as such, it is 90% loaded. So this is well within the maximum power carrying capacity of the line. Now, another example you can see. So this is load reduction. Why it is called as load reduction? When looking from the grid side, what is the effective load this side? In the first case, which is 15 kilowatts. Now in the second case, what is the effective load? 15 minus 6, which is 9 kilowatts. So this is load reduction. Okay. Now in the second example, you can see more local power is there. From the local power injection is in excess, so we can pump it to the grid. So the direction of power has reversed, and still 15 minus 1 is 14. So 140% overload is there for the line which is connecting the local node and the grid point. Now, what can be done is this 15 kilowatts is now reduced to 10 kilowatts. Here, in the first example, what is done is some electric vehicles are participating in the discharging activity. Okay, in the V2G support. Here, some more electric vehicles are participating in the charging activity. That is why some consumption is there from this side. So 15 kilowatts generation was there from here, this parking lot. This is a pooled parking lot. Now it's only 10. Okay. So when it is 10, this is only 90% loaded, right? 10 minus 1 is 9. So 90% loaded. So this is kind of peak shaving. At peak load periods, this can be used as a flexible source. So this service can also be incentivized. The grid owners, the EV owners can earn from this activity also, similar to the frequency regulation activity, but a portion should be given to the aggregator. Now going to the next one, voltage regulation. Two examples are given here, voltage regulation example 1 and voltage regulation example 2. So on top you have example 1, in which 100 kilowatts is the generation from the discharging EVs which are pooled in the parking lot. This can be like discharging minus charging power. Some of the electric vehicles are charging and some other electric vehicles are discharging, but the net discharging power is 100 kilowatts. That can be the case also. Now 500 kilowatts is the load here. So 400 should come from here, right? From the grid. So when 400 comes from the grid, you can see that the voltage profile of the local node is a bit on the lower side, which is only 86.1%. But your tolerance is plus or minus 10%. So it's outside the tolerance limits, right? If it is in between 90% to 110%, we would have made it inside the limits, but now it is only 86.1%. So how to improve this scenario? So we are, if this parking lot has inverters with reactive power control capability, then instead of 0 kVAR producing from this point, you can have 200 kVAR produced. So when 200 kVAR is produced, you can see here, the whole 200 kVAR local reactive power demand is completely satisfied from the local parking lot. It's not, nothing is coming from the grid side. So from the upstream grid, we are not depending on the upstream grid for reactive power demand. So by this, we have improved the voltage profile to 88.6%. Now active power control. So now it is only 100 kilowatts. Discharging electric vehicles contribute to 100 kilowatts generation. Now we are increasing it to 200 kilowatts generation. So it is now well within the limits. 91.8% is the profile. That is 0.918 is the per unit value of local voltage, local node voltage. So it is within the limits. So this flexibility is used here for voltage regulation. This can be another ancillary service which is charged. That also is an avenue for earning. Now in the example 2, what happens is the direction of power is reversed. The direction of power flow is reversed. So 700 kilowatt is produced from here, 50 kilowatts is the load, right? So the excess is going to the grid. So what happens here? There is a voltage swell, right? 14.1%, 14.1%. That means 4.1% outside the tolerance limit. Now, because within 110% means it's fine. Otherwise, this plus or minus 10% tolerance is not satisfied. Now, what is done is here minus 200 kVAR. That means here reactive power consumption is there, right? Reactive power consumption in the sense if the inverter is capable of reactive power control, some reactive power demand is made here, and the voltage profile of the local node is reduced to 112.2, but still it's not satisfied. Now what is done is this 700 kilowatts power, active power, is reduced to 500 kilowatts. So again, some more electric vehicles are removed from the discharging mode. It can be moved to the other mode, the charging mode also. So this 500 kilowatts is, because of this 500 kilowatts, this now is reduced to, the local load voltage profile is reduced to 108.2%, which is well within the tolerance limit. Now, reliability improvement. So we know that active distribution systems, if they are self-sustained, can be intentionally islanded or unintentionally because of some fault also, it can be islanded. But in the islanding operation or in the islanding mode, again, the generation demand balance should be met or satisfied. So in the first case, you can see that 20 kVA generation is there from this point, and the load is 15 kVA. Then here one more load is there, 25 kVA. So the total is 40 kVA. The total load is 40 kVA, and 20 kVA is only the local generation. So remaining is coming from the grid, the upstream grid. Now we are going for the full islanding, not partial islanding. We are going for full islanding. So when going for full islanding, what you can do is these electric vehicles, some of the electric vehicles which are available here can be put on the discharging mode, and 30 kVA is produced from here. So 25 plus 15 is 40, right? 30 kVA is the capacity from here. 30 kVA is the capacity here. So 20 kVA can actually be dispatched. So what should be done here is, before the islanding process itself, if they are planning for an islanding activity, from the parking lot, it should be communicated that up to 30 kVA support can be given from this particular parking lot, 0 to 30 kVA. Okay, 30 kVA, up to 30 kVA capacity can be supported from the parking lot. But again here, the issue of availability of electric vehicles and uncertainty in state of charge because of the uncertainty in trips and travels of the electric vehicles is there. That we'll see. We'll address these problems in the coming slides. We are just going through the framework now. What all are the possibilities and avenues with the EV owners? So with the 30 kVA, with the 25 plus 15 is now 40. So 20 plus 20. Here, if 20 is dispatched, then it can be completely met from the local generation. Of course, some loss is there. So for meeting the loss also, this can be used. Okay, because here why we are depending upon electric vehicle parking lot is that this source may be a renewable energy source. So according to the real-time availability only, this can dispatch. I mean, this is a non-dispatchable source, right? According to the availability of the natural resource only, this will generate. So the remaining can be taken from the electric vehicle parking lot. Now, here in the second case, what happens is, this is 25 kVA. Okay, so now 20 kVA is produced from this point, 25 kVA, this is in charging mode. So 25 plus 15 is 40. This is in charging mode. So the local generation is only 20. So remaining 20 is coming from the grid. Now, when we are going for partial islanding, suppose full islanding is done, what happens is the total load is 15 plus 25. If there is no load flexibility for this particular load, then 15 plus 25 will be 40. 15 is only locally produced. But as this is a flexible load, what you can do is some of the electric vehicles can be plugged off so that this can be partially islanded. 15 kVA is the local generation that is available from the renewable energy source, and 15 kVA is the load. So obviously there should be some storage provided here, otherwise islanding is not practical. This is just a case study to explain what is the importance of flexibility of the parking lot. Now, so peak shaving, frequency regulation service, voltage regulation service, reliability improvement, these are the things. Now we will move on to the next part, the EV challenge, certainty and uncertainty. So when we purchase the EV, you can see these blocks which show the actual challenges with EVs or even opportunities with EVs. So at the time of purchase, there is a capital investment which is very high, right? So, but to connect it to the grid, we have to, anyway, for the charging infrastructure also there is an upfront cost, but obviously you will get some subsidy based on the regulator, whoever regulates the system. If he gives some subsidy, then it's fine. Now, there is savings in emission during operation. While operating EVs, we know that there is savings in emission, but how it reflects to the end consumer, that reflects in terms of subsidy only, right? While operating, of course, fuel cost is not there, but the reduction in emission is not directly reflecting on the EV owner. He gets a subsidy for the upfront cost, that's all. Now, but what happens to the aggregator or the utility? If the utility is sourcing power from electric vehicles rather than replacing some conventional fuel-based sources, then what happens is the total carbon emission of the system is reduced. So for the utility, he may be incentivized or his penalty may be less based on the reduction in CO2 emissions. So this indirectly reflects on the utility. Financial impact is there on the utility, but direct financial impact is not there for the end consumer based on operation. For purchase, of course, it is there. Okay. Now, B2G revenues, we have already seen through different ancillary services and grid support activities, the owner is getting some revenue. So based on that, he can invest. Now, G2V cost, obviously for charging the electric vehicle, it reflects on the electricity bills, right? So that is a major operational cost. This has to be properly studied before investing on the EVs. Now comes carbon life cycle. This is, see, we say that when we replace a gasoline-based vehicle with EV, with respect to operation, there is carbon reduction. But as far as that product is concerned, what is the life cycle carbon emission for that product? That is calculated from the manufacturing phase itself. So while manufacturing the EV, if we have, if we depended on conventional fuel-based sources for power supply, then there is some indirect carbon emission is there. So when considering the carbon footprint of this product, it is more. We don't know how much it is there. That has to be compared with the gasoline-based vehicle, and we have to analyze it properly. We have to study it properly. So this is another of EV. Then maintenance cost. Maintenance cost, of course, is less for EVs when compared to gasoline-based vehicles. Then policy framework and aggregators preference. This is a very important aspect. As per policy framework, suppose you are not allowed to participate in the V2G activity, then that earning is completely, negated, right? That is not there. So the revenue is affected. The operational side revenue is affected. So the lifetime revenue is affected. So that affects the net present cost also, net present revenue also. So the policy makers' decisions are very important while investing on the EVs. Then the charge for regulation services, the charge for all other ancillary services, all these are important. Sorry. Now, warranty on battery. See, for any EV, there is a warranty on battery. But if suppose the supplier of the battery says that if you participate in the V2G activity, your charging and discharging cycles, number of cycles are more, right? then the warranty is not valid if you participate in V2G activity. Then you cannot go for that, right? Because the battery life is less. It'll be reduced when you go for V2G activities, and you will need to replace the battery. So that cost should be considered in the net present cost. It should be accounted in the net present cost. Then benefits over gasoline. We have to compare everything with the gasoline based vehicle, and we'll see the net present cost. Trip uncertainty and charging and discharging uncertainty, which we have already discussed. We are planning these things in the entire lifetime of the EV. This much capacity can be committed for frequency regulation and all, but in actual time horizon, if it's not possible, then the revenue may be affected. There is an impact, financial impact, in the revenue. Now, you see here the net present cost. What is net present cost? It depends on the discounted cash flow. So here what we have modeled is, compared to the gasoline based vehicles, how the revenue and expense for the EV differ. That is what we have considered. EV cap is the capital cost on EV or the upfront cost on EV. So all positive signs, positive terms here are costs, and all negative terms are revenues. Okay. So maintenance of EV is a maintenance cost which is positive, right? Now, fuel cost compared to gasoline. That means fuel cost of EV minus fuel cost of gasoline based vehicle. You have some other vehicle in your mind, and you want to compare both and find the net present cost and whether it is feasible or not. This is financially feasible or not. You are studying, and then only you are going to invest on EV. So EV capital cost, EV SE capital cost, which is the charging infrastructure cost. Some charging infrastructure cost is there for this. So EV SE cap minus gasoline capital cost. So this is the upfront cost for the gasoline based vehicle. So this is a saving basically. So this is cost for EV, this is cost for gasoline. If the total, this first term, the net value of the first term is negative, then what does that mean? The gasoline based cost is more, right? Otherwise it will be positive only, right? Now in the second term, fuel of EV minus gas, which you have already considered, then maintenance of EV minus gas, this is the battery replacement cost, and this is the discounted rate. That means 100 rupees spending now and 100 rupees spending after 1 year is different, right? The value is different. So based on that, some discounted rate is there. Discounted rate is there. That is this R, and Y is the total years of lifetime. The total lifetime of the EV in terms of number of years. So based on this, we are calculating the net present cost, and we are arriving at a decision whether to buy EV or not compared to a gasoline based vehicle. Now, okay. Now, we have seen here in this green block, policy framework and aggregators preference. How that affects our decision on purchasing EV. That is, if the utility of your distribution network, that means the distribution network in which you are going to connect your EV for V2G activities, the utility there, he prefers more of, his preference is economic preferences rather than environmental preferences. Then he may go for some other sources. We don't know, because if other cheaper sources are available, he will go for that. He will not take this green concern into his consideration. Okay, so he may not give importance for EVs. So V2G activities may be less paid at that time. So the aggregators policy framework is very important. In that case, we'll see how the objectives are put forward by the utility or the distribution system operator in the microgrid. You see here, this is economic mode. If the microgrid is working in economic mode, the system operator gives more preference to economics. That means the objective function is basically DG operation cost and revenue. Suppose revenue that he gets from the operation minus the expense for the DG operation gives his profit, right? Whose profit? Utility's profit, or distribution system operator's profit or aggregator's profit. So he wants to minimize this. This is his objective function. If it is profit, then maximization. If it is cost, then minimization. So he has economic objective in mind. So accordingly, his constraints differ. Of course, he has GHG emission, carbon emission and other things, but his prime motive is economic objective. So here he considers DEG physical limits, that is, every distributed generator has a minimum and maximum limit of generation that is considered. Then energy balance is an equality constraint, right? Generation minus demand minus loss is 0. So this is energy balance constraint, right? So these two are technical constraints. So this actually goes to he's not very stringent with this. He is not giving more importance to the technical constraints. He just says that maybe 10% tolerance is enough for me, but I am giving more importance to the profit side. So this also affects the decision of a buyer who is residing in this particular microgrid as a residential, EV owner, whether he buys EV or not. Now, coming to the technical mode, what happens in the technical mode? As I already explained, technical mode can be voltage deviation minimization or loss minimization or something else. So here he has considered loss cost. That means network loss represented in terms of cost. He is trying to minimize this. So this actually may completely keep away the V2G activities, because your location in the network, even that, has an impact here. Because if you are farther from the substation, then you can contribute more to voltage regulation services. If you are nearer to the substation, you may not contribute much to the voltage regulation services. So he is completely looking at technical things. We don't know whether buying an EV is a valuable proposition or not. That also comes into consideration here. But his constraints are now stringent. Maybe he has put some plus or minus 2% tolerance for grid voltage and loading, DG physical limits. It follows, but aware of the environmental concerns and the economic concerns. He just have a limited preference for that. Now, in environmental mode, the loss cost has shifted to emission cost now. So he is completely concentrating. This particular operator is completely concentrating on emission cost. So he is giving more importance to renewable energy sources. He is giving more importance to EVs, V2G activities. And in constraints, he is not that stringent about the grid voltage and loading constraints. Rather, he is looking more at DG physical limits and energy balance at a medium level. At a moderate level only, he is looking at these constraints. So these things are also important while going for V2G activities. Now we'll move on to we'll move to the next step, where actual scheduling happens and what are the challenges of scheduling. You can see here a system which is the SIGRE LV benchmark microgrid, which is normally used for microgrid studies. This is a test bench system. Here you can see the first one, the leftmost feeder is a residential feeder, then the middle one is an industrial feeder, and the rightmost one is a commercial feeder. So the residential feeder has local distributed energy resources. You can see here micro wind turbines are there, rooftop solar PV sources are there, then fuel cell is there, then micro turbine is there, diesel generator is there. So costly sources are there, cheaper sources are there, uncertain sources are there. So in addition, suppose you have EVs also with all these are residential loads, right? So group of 4 residences are here, then single residential customer is here, apartment building is there. So pooled parking lots, the opportunity of having pooled parking lots and pooled power injection from these nodes, if that has to be utilized properly, then they can buy electric vehicles and they can have it. But we'll see what happens now. So these people residing at the residential feeder, in the morning, they move to the industrial feeders and the commercial feeders for work. Then evening, they come back. So the timing for the schedule of these EVs, the normal schedule of these EVs are given here. That is the information given and information communicated from the intelligent parking lots. We have already discussed about smart parking lots. The information provided from the intelligent parking lots are given here. That is from 1 to 8 hours. At these nodes, number of EVs are given. Okay. Now 9 to 18. At these nodes, number of EVs are given. This is just an estimate because this is communicated prior to the actual transaction. This is the commitment, scheduled commitment. That's all. Now, so 3, 12, 13, and 8. 3, 12, 13, and 8. These are residential nodes, right? So at these nodes, the number of EVs are 1, 15, 4, and 10. So the trip time is also given here. Trip time is from 8 to 9. So 1 to 8, it is available in the parking lot. 8 to 9, it travels, right? After traveling, it reaches the workplace. So the workplace is either in the industrial feeder or the commercial feeder. So accordingly, the number of EVs are expected like this in those parking lots. Okay. Now, again, I mean, from 18 to 19, that means 6 p.m. to 7 p.m., it travels back to the residential feeder itself. So at night, these vehicles are supposed to be available at the parking lots. Now you see, this is just based on their routine. They can take their vehicle for some other purpose. If there is an urgent trip, a hospital trip or something else, it may not be available there. So this number of EVs estimated may change. So if these number of EVs change, what will happen? That will reflect the power injection at that particular node. Suppose there is an apartment load here, right? Some 10 EVs are here. I mean, 10 EVs are supposed to be here at a particular time period, but 3 EVs are moving out. Then this affects the power injection at this particular point. But the operator cannot wait until that time, the real-time horizon, to have this contingency. Rather, what he can do is he can run a load flow with the available information from the intelligent parking lots, as well as the available information from the load forecasts and renewable energy forecast. So many renewable energy sources are here. Solar and wind energy sources are here. So based on the future forecast of the renewable energy generation, they can communicate the operator. Based on the availability of EVs in the parking lot, these intelligent parking lots can communicate with the operator. Similarly, for load forecast can also be done by the operator. So based on this, he is executing a load flow. So normally we know that load flow is a deterministic static tool, right? Because when you run Newton-Raphson load flow or Gauss-Seidel load flow, Gauss-Seidel method, load flow using Gauss-Seidel method, you assign each bus as a PQ bus or a PV bus or a slack bus, right? So for a PQ bus and PV bus, P is fixed, active power is fixed. For a PQ bus, reactive power is also fixed. For a PV bus, voltage is fixed. So if based on these forecasts, you are executing the load flow, your power injections at each bus depends on your assignment of that particular bus, right? Your assignment in the sense PV, PQ or slack. So wherever there is uncertainty, you assume that uncertainties are buffered by the slack bus. That is your assumption. So now with these uncertainties in power injection, we have to incorporate these uncertainties into the load flow also, right? So slowly the deterministic load flow approach is moving towards a stochastic load flow approach. What is stochastic load flow approach? We'll see. Now, before going to the load flow, we need to know the objective of the utility also. 1 minute, let me check the time. Okay, objective of the operator also. If his objective is profit maximization, suppose, okay, we'll discuss that in the next slide. Before that, so if it is cost minimization, then a function of cost, you should frame the cost function as a function of independent variables, active power, independent variables as active power dispatch from each of these sources. Because when active power output from these sources vary, accordingly the operational cost is varying. So if you want to minimize the operational cost, you have to get the optimal values of power outputs from each of these sources. But now we see that the independent variables themselves are random. They are not deterministic. They are not just P1, P2, P3, etc. P1 can vary in a range, P2 can vary in a range. So these values are basically stochastic variables. So based on that, we have to run optimal power flow. So we have already discussed about load flow. Now into this load flow, we are incorporating an optimization problem also based on the preferred objective of the operator. So it becomes an optimal power flow problem. Basically, before the real-time horizon itself, the operator runs the optimal power flow problem and he gets the dispatch set points, and this is the schedule of the microgrid. Now, the efficient schedule. What about an efficient schedule? What should be an efficient schedule? An efficient schedule should be more practical. That means in real time, much deviations should not be there from the schedule. So it should be more realistic. We'll see how we'll make it realistic. Okay. Now, in this particular system, the aggregator or the DSO is the third party. The same framework which we discussed in the second slide. The third party purchases power from different sources. It can be discharging electric vehicles. It can be renewable energy sources. It can be fuel cell, diesel generator, micro turbine, anything. It purchases power from these sources and it sells it to the end consumers. So his revenue is, third party's revenue is obtained from the end consumers or the charging electric vehicles, because charging electric vehicles consume power, right? His expense is for buying the power from these sources, right? These sources, these generation distributed energy sources. So his revenue minus expense, if you could model it properly, that is his profit, the third party's profit. And the third party schedules the sources for maximization of his profit. Let's see how it can be done. Okay. So the expense of aggregator, you can see the function here, expense of aggregator. The conventional distributed energy resources. What are conventional distributed energy resources? So these are fuel-based distributed energy resources. That means diesel generator has some operational cost, right? Whoever owns a diesel generator has some operational cost based on the fuel price. So based on that, he might have set a price for his power output. So this is given by the aggregator and he purchases power from the diesel generator, right? Similarly, from all conventional DERs, conventional distributed energy resources, they have all submitted a bid to the third party. Based on that, there is a cost for the aggregator. Now, what is the second term? So now we are formulating the expense of the aggregator only. So all these terms are cost for the aggregator. So cost of purchase from renewable energy sources. So renewable energy sources, we only, so P is the active power corresponding to the forecast. This can be P wind or P solar. Okay, in general, I have mentioned here P REN, that's all. Now, there can be uncertainties in this particular power. So that is why it is one more variable is included here, UN REN, uncertainty in renewable energy. So P REN can move to both sides. Suppose your forecast is 5 kilowatts. In reality, or from the historical database that you have, you see that you have a maximum deviation of 20% to both sides from the forecast. That means this UN represents plus or minus 20% deviation of this active power. This is forecast, but there can be deviation from the forecast, right? So this is basically a random variable, P REN. Now, cost of purchase from grid, P grid. So P grid is actually a deterministic variable. I mean, inherently a deterministic variable, because grid is a very, it's a bulk power system. So we assume that power can be taken whenever needed from the upstream. Simply a deterministic variable, but what happens is, if there is an uncertainty in this power from renewable energy, it has to be balanced from the grid, right? So indirectly, the uncertainty in renewable energy reflects on the grid. So this also becomes a stochastic variable, which is a function of P run. Okay. So if P grid is stochastic, then cost of purchase from P grid is also stochastic. That means this is also uncertain. So each term is now becoming stochastic variables. That means the expense of aggregator, we cannot say that we will get, the aggregator gets this much, or the aggregator's expense is this much for a particular hour. We can only say that the aggregator's expense can be in this range based on the uncertainties of renewable energy sources, loads, and electric vehicles available in the parking lots. Now, there is a load curtailment activity also. Owners have informed the house owners, the residential consumers have communicated with the operator that some of our loads are flexible. So for this load curtailment, they are incentivized. They are given amount. Expense for the aggregator. He gives money and he's only incentivizing them, right? Now, amount given to discharging EVs, right? For discharging EVs, it is purchased by the aggregator, so that is also there. Now here also we have included one uncertain variable, UNVD K. For the kth electric vehicle which is under discharging mode, there is an uncertainty. So this uncertainty can be of three types. That is the state of charge, that is the already committed EV. That particular EV not available in actual time horizon. That is one case. Then another case can be the number of electric vehicles which are committed for discharge was 12 in a parking lot, but in actual time horizon 7 are only available. So in number of electric vehicles also uncertainty can be there. Then what can be there? Another thing, it indirectly affects the state of charge itself. We assumed some trips. We planned travel by use of the electric vehicle, but our travel distance is somehow different. So based on that also, the state of charge can be affected. So that also falls under the uncertainty in state of charge. So this is also a stochastic variable. So this is the expense. Now what is the revenue? As revenue, he earns from the grid. If he pumps power, excess power to the grid, he gets something, right? So that is one of the components of revenue. Then earning from sale of power purchased from DERs. From all these distributed energy resources, he has purchased power, the third party, then he is selling it to the consumer, so he is earning, right? Now earning from sale of power purchased from renewable energy sources. From renewable energy sources also he is buying power and he is selling it. So from there also he is getting some revenue. Now earning from sale of power purchased from discharging EVs. Then amount from charging EVs, right? So for all these contribute to the revenue of the aggregator. Now revenue minus expense, if you take, you will get the profit. Now profit is a function of power, active power. What is this active power? This is not only one variable. This is a vector. Okay, that is P1, P2, P3. How many sources are there? That many active power outputs are there. So this profit is a function of these powers. So our aim is that we have to maximize the profit so that we can find the optimal values of P1, P2, etc. up to Pn. If n, it is an n-dimensional vector, then P1, P2, etc. Pn. So we are finding P1 star, P2 star, etc. up to Pn star, optimal values of active power outputs for which the profit of the aggregator is maximized. So this is the schedule as far as the aggregator is concerned. So the aggregator is trying to frame the schedule in a realistic manner by considering these uncertainties into account. Okay, now we will see what are the constraints. We can see the first term, which is sigma mkt equals tpk. What is this? See, are you able to see this term?
Yes, sir.
Yeah. So now The total duration in which the vehicle is available in the parking lot is the difference between the departure time and the arrival time. So the arrival time is TA. For the kth electric vehicle, it arrives at time TA and it is there up to time TD, right? So this is the total duration. But in the total duration, we don't know how much time it was in the charging mode, how much time it was in the discharging mode, how much time it was in the idle mode. Three modes are there for each electric vehicle, right? So this MKT gives the mode. It represents the mode of kth electric vehicle at time period T. Okay, so if this is a multiplication factor for active power output from that particular electric vehicle, then if it is in idle mode, this M will be 0. There is no power output, right? Now, if it is +1, if positive power output is, if the power is injected from the, or discharging power is considered as positive, then the vehicle is in discharging mode, right? If this M is -1, then it is in charging mode. So this is basically a representation of vehicle charging, discharging, or idle mode, which is a multiplication factor. Okay. Now, according to the life of battery, we have charging and discharging rate limits. You cannot charge or discharge the battery at any rate. So there is a delta state of charge for max and max for any kth electric vehicle at time period T. So we see these variables, these decision variables, active power values P1, P2, etc. They are not just free. We cannot just explore any value of P. Within these constraints only, you can search for constraint stochastic optimization problem, which includes load flow also to check the network feasibility. We'll see the load flow part later, but now we'll go through the optimization problem. Now, as a third constraint between charging and discharging mode, because you cannot switch between charging and discharging mode infinite times. There is a limit for that based on the battery specification, battery life, the health of the battery. So we have to follow that constraint also. Now, stored energy of the kth electric vehicle at time T based on SOC. So the energy corresponding to the state of charge of kth electric vehicle at time T depends on the energy corresponding to state of charge of the previous hour. This is T-1, right? At the previous hour, it was it might be on charging mode or discharging mode. Based on that, some energy is there. It's already available. Now, what happens in this particular hour? That is delta E. Okay, so E, the energy that is the the outcome of the previous slot plus the delta E, what is happening in the at present, what is happening at present. That is what is considered. So charging is considered, efficiency of the at the discharging mode is considered, and it is multiplied with the power, discharging power and charging power, and this is energy which is dissipated when the trip. During trip, this is the energy that is dissipated. So these are positive values, right? And this is negative. These two are negative. Discharging values are negative, charging values are positive. So this is the current energy corresponding to the present value of energy corresponding to the present state of charge at tth time for the kth electric vehicle. So this is equality constraint. These two are inequality constraints. So these two inequality constraints should be satisfied. This equality constraint should be satisfied. This equality constraint should be satisfied. And we have maximum and minimum percentage of battery capacity considering battery life. We know that the depth of discharge is not 0. For some battery, it should be 20% discharged. The minimum state of charge should be 20%. So for some other batteries, it is 30%. So based on that, this should be fixed. And maximum can be 90 for some batteries. For some batteries, it may be specified in the manual. So based on that, we have to operate in between. So the discharging power and charging power of the EVs, which are, some of the decision variables in this profit, they are not just free. We cannot search any value for those variables. We should search all these powers, we have to check whether this is network feasible or not. We have obtained power output from fuel cell, diesel generator, micro turbine, from each parking lots, everything we got. But these are different nodes, right? Parking lots are different nodes. Then fuel cell is a different. It is connected to a different node. Diesel generator is connected to a different node. So basically, these power injections, we already got these power injections, and we know the load forecast on the load flow. So we have to know whether this is network feasible or not. How to do that? We'll see. This is uncertain profit. We'll come back to this after the load flow part. Okay. Interval uncertainties in EV power injections. How will you incorporate interval uncertainties into power injections while executing load flow? So you see here the definition of upper and lower limits of intervals are given below. So EV is connected to a particular node. Power injection because of EV discharging, right? EV discharging modes. So this power can be a maximum of P upper bar or can be a minimum of P lower bar, because we know that there are uncertainties in EV power injections based on the uncertainty in state of charge and number of vehicles available in the parking lot. So at this particular node, we can only say that the power injection can be in the range of minimum to maximum. So these values you can generate either from the historical data, or if it is solely for study purpose, you can generate it, randomly generate it using Monte Carlo simulation or other methods and fit it into some standard probability distribution functions. We will see it later. Okay, so this is basically the range of power injections that can be there from that particular node. Okay, similarly for demand also there is some range, so it is represented in terms of intervals, right? Now what is PGEV? PGEV is PGEV naught plus epsilon. What is PGEV naught? This is the committed value from a parking lot for to the operator. We say that from this parking lot, these many EVs are supposed to be there. Number of EVs are 7. So based on 7 EVs, this is the generation that is possible. So this is basically the estimated value, but we can have an error, right? So this error is sigma EV positive. This is to the positive side. This error to the positive side. This is error to the negative side. So while considering the error to the positive side, we get the P upper bar, the maximum limit of the range, and the minimum limit of the range we obtain by taking the negative direction. So what happens here? We know that we'll see. Okay, we know that while running load flow, what is a basic complex power equation? VI conjugate, right? V is a complex value, I is a complex value, S equals VI conjugate. Now you see here 3 nodes are given: VK, VI, VJ are the voltages of kth node, ith node, and jth node, and the currents are IKI and IIJ. From current, the current from I to J and current from K to I. Now what is IIJ? IIJ equals IKI plus what is the injection from node I? So the current injection from node I plus IKI will give you the IIJ. How to find the current injection from node I? Current injection from node I is Pi minus JQI by V star. This is S star by V star. Okay, S equal to VI star, S star by V star is I, right? So I injection. So current injection from here plus line current IKI will give you IIJ. But the problem is this current injection is uncertain. This is represented in terms of interval using interval arithmetic. So basically what you have is I lower bar and I upper bar based on the, if only electric vehicles are there in this particular node, based on the maximum and minimum active power that is generated by discharging electric vehicles at that particular node, we have an upper limit and lower limit for current. So current is an interval there. Current is an interval. So IIJ bar is there, IIJ upper bar is there, IIJ lower bar is there. So throughout the execution of load flow, wherever addition, subtraction, multiplication, whatever comes, it is in terms of, it is using intervals. We are doing it using intervals. We are not using two different values. We are using two different ranges. We are not, it's not like A into B. It's interval of A, which is A lower bar, A upper bar, into interval of B, which is B lower bar, B upper bar. So this is interval arithmetic. So how interval arithmetic is done? Interval arithmetic operations are done. That is what is shown here. So if two intervals are, how to add two intervals, how to subtract two intervals, and how to divide two intervals. These are basic arithmetic operations. Okay. So, so the full load flow will be executed in interval operations. So what will be the output? The output will also be in the interval form. You cannot say that a particular profit is can be obtained by the aggregator. Rather, you can say that the maximum profit can be this much and the minimum profit can be this much. For each nodal voltage, you can say that the maximum voltage can be this much and the minimum voltage can be this much. The line loss, the total network loss can be P loss max and P loss min. So this variations in decision variables, these output variables are based on the uncertainties in power injections due to renewable energy, electric vehicles, loads, etc. So we are incorporating the uncertainties into the load flow equations. That is what we do using interval arithmetic. So now another aspect. In addition to interval uncertainties, we are going to consider sensitivities also. What is sensitivity? See, if there is an uncertainty in power injection at this particular node I, that will somehow affect the power injection of node J, right? This happens for active power and both active power and reactive power. So for this, to account this, we are considering sensitivities also. How to consider sensitivities? Let's see. So now we are defining the variable as, earlier we defined it as interval, right? So every current was in terms of interval, or was represented as interval. Every active power value was represented in terms of interval. Reactive power was represented in terms of interval. Now everything is represented in terms of affine values. We'll see what is affine values. So affine current Iij, this is a line current. Affine current Iij equals Iij0. What is Iij0? Iij0 is the current, the line current corresponding to deterministic scenario. What is deterministic scenario? Without any uncertainties. That is certain current Iij0. That means if we are depending completely on the information that is coming from the parking lot and you are assuming that this is accurate, then you will get some current, line current. That is what is Iij0. Now there can be error in the power injection of the parking lot, right? For the kth node, a parking lot is connected. If a parking lot is connected to the kth node, there is an uncertainty in the active power injection from the kth node. So based on that, there is some error. So based on this error, this Iij can deviate. So based on the active power injection uncertainties from the kth node, what is the change in Iij, line current? What is the sensitivity of line current Iij based on the uncertainties in the nodal power injection, nodal active power injections? Similarly, there are uncertainties in the nodal reactive power injections also. That also affects the line current. That is what is the second term. So basically, the first term is deterministic value, which completely depends on the depends on the forecasted values or estimated values. And the first term, the second term is the sensitivity of this value because of the uncertainties in active power injections from the kth node. And the third term is the sensitivities of line current with respect to reactive power injections from the kth node. Okay, so finally we'll get the Iij affine. So Iij affine is basically the real part of current plus J into imaginary part. Okay, so by using this current, you are finding the receiving end voltages, because if you know this voltage, V minus Iij into Z will give you the Vj, right? So based on this, all the variables are becoming affine now. because for deterministic value, there are some voltage values. Corresponding to deterministic estimates, there are voltage values. That will be UI 0. Okay. Now, based on sensitivities, we have some delta UI. So delta UI with respect to active power injection uncertainties, delta UI with respect to reactive power injection uncertainties. Both are considered, and you are getting the affine voltages. So affine voltages, affine currents. So here both interval as well as sensitivities are incorporated to the load flow. So that will reflect on the complex power that is flowing and complex power loss, etc. everywhere. So these are the only, I mean, I'll emphasize on these two terms only. IIJ-PK is line current IIJ because of the line current IIJ because of the uncertainties in power injection at kth node. Okay, so dou IIJ by dou PK. Whenever there is a change in kth power injection, kth node power injection, active power injection, what is the change in IIJ? This is the sensitivity of line current with respect to nodal power injection uncertainties at the kth node. Okay. Now, similarly for reactive power injection uncertainties also, IIJ is affected, right? IIJ KQ. Okay. Now, what is this? How to find this dou IIJ? IIJ n minus IIJ 0. IIJ 0 completely depends on the forecasted values. Whatever is given, whatever information is sent from the parking lots, whatever is the forecasted value of renewable energy, whatever is the forecasted value of load, based on that, if you run the load flow and if you find the current, line current, you will get IIJ 0. But IIJ n is for the uncertainty. That means you are slowly changing, perturbing the active power injections from each node based on the uncertainties. P plus delta P you are doing, or P minus delta P you are slowly incrementing or decrementing the active power. Based on that, you are again running the load flow, you are getting IIJN. Okay, the new value. Now divided by delta PK. Delta PK is a change in power injection. Whatever is the change you have inflicted on the nodal power injection, that is this one. So like that you are getting the sensitivities also. So so far we'll just revise this part. We started with the different services that can be provided by the V2G activities by purchasing electric vehicles, and the functionalities of electric vehicles on ancillary services, voltage regulation, peak shaving, reliability islanding, frequency regulation service, etc. Then one frequency regulation service case study we have done. Then what are the possible uncertainties in revenue based on the price variations or power capacity of electric vehicles or EV availability in the parking lot? How to incorporate that? Then the basics of peak shaving, voltage regulation, reliability improvement, and the net present cost, evaluation of net present cost of EV, considering the V2G activities and comparison with the gasoline based vehicle, whether we should purchase it or not, arriving at a decision on that. Then the preferences of aggregators, the objective is whether it is economic or technical or environmental. Based on that also we have to, that also impacts on the decision of purchasing EV. Then we had discussed about the SIGRE LV benchmark microgrid system, in which 3 feeders are there, and the routine schedule is given here. Based on that, we set an objective. Maximizing profit is the objective that is set by the aggregator. So modeling the revenue of the aggregator, expense of the aggregator, which is as a function of active power outputs as decision variables, finding the optimal value of profit for the corresponding values of active powers, and communicating this as a schedule. Now, how to make it more realistic, how to make the schedule more realistic, we have to incorporate the uncertainty models into execution of load flows for getting a realistic network feasibility result. So first one was interval uncertainties, to represent all variables in terms of intervals. Then the second was, in addition to interval uncertainties, we are taking the sensitivities also into consideration, how to consider that in the load flow problem. Now, we will move on to the last topic, which is probabilistic analysis or the concept of value at risk. Let me check the time. It's 4. Maybe in 10 minutes I'll wind up. So now we have seen that all the variables were represented in terms of intervals, right? Suppose for EV connected nodes, we know that the lowest possible value of power injection is P lower bar, and the highest possible value of EV power injection is P upper bar. But in between these values, any value can be taken, right? That means suppose this is 5 kilowatts, this is 10 kilowatts, 6 can be taken, 7 can be taken. We only say that in between these two values, any value can be there at that particular nodal power injection. But we don't know about each value and the corresponding probability, because sometimes there may be more probability to take the value 7 when compared to a value 8, right? So if that also is taken into consideration, then we can model or we can draw a probability distribution function in between these two values. Suppose this is 5, this is 10. In between 5 and 10, we can draw a probability distribution curve based on the historical values. Sometimes 3 electric vehicles would be there. Sometimes 7 electric vehicles would be there in the parking lot. Sometimes 8. So we have this database with us, right? Based on this database, you can fit probability distribution function to a standard distribution curve. So we have the probability values of all these active power values in between these two limits, and the extent of range is dependent on the minimum and maximum values. If it is 2 to 10, it is an extended range. If it is 3 to 6, it's a shorter range, right? So we need not take all the values. Low probable values could be negated. That could be cropped out, and we can make the interval shorter. So it will become more realistic then. If you only know that at a particular node, the voltage of that particular node can be from 0.5 to 1.5, then it's an extended range. Rather, if you are informed that it is between 0.8 to 1.2, the range is shorter and the decision is more easy to be taken. So if you model the probability distribution of these ranges, then you will get a better idea or more practical schedules you can produce. Let's see what is concept of value at risk. Here the horizontal axis shows some random variable x, and all these are the values that can be taken by this random variable x, and the corresponding probabilities are fitted to some standard probability distribution function. Suppose, what is this random variable? Suppose we assume that this is number of electric vehicles in a parking lot. So every day you see that this value is varying, right? Sunday you see that 3 vehicles are there. Monday when you see 6 vehicles are there. Tuesday it is 8. So it is different. Every time it's different. So this uncertain variable is modeled by probability distribution CARA. So based on the historical value, you know that which all numbers have higher probability and which all numbers have lower probability, right? If you commit with 10 electric vehicles, you always see that 9, 8 and 7 has higher probability maybe, but having 3 electric vehicles or 2 electric vehicles might have lower probability. So to get this information, we are drawing the probability distribution CARA. Now, value at risk says that the definition of value at risk is that at a particular confidence level, we can say that at least this much electric vehicles would be there. That means at 95% confidence level, 95% confidence level in the sense this area, that is the total area minus this lined part, this barred region, that is this one. The total area gives you the 95%. This is 5%. Okay. So with 95% probability or 95% confidence, you can say that at least this much electric vehicles would be there. So analyzing all the historical values in the database, you say that at least 3 vehicles will be there in the parking lot, I can say that with 95% confidence level. Now, if you increase the confidence level from 95 to 98, then what will happen to the value you are getting here? If you are again increasing it, then this range is increasing, right? 90, this is 95, now it is becoming 98, means it goes to here, right? 98%. So now certainty is more. With more confidence, certainty is more. With more certainty, we can only say that some 2 vehicles will be there. That is definite. With 98% probability, I can say that 2 vehicles will be there. At least 2 vehicles. That means, so the risk, the value at risk is defined as the value that can be taken by the random variable at a particular confidence level. So that is what the value at risk says. This is one model. Now, one more last slide here. Uncertain profit of the aggregator. See, this is percentage uncertainty of state of charge of electric vehicles. Horizontal axis shows the percentage uncertainty in state of charge of electric vehicles. What is 0? 0% uncertainty means what? Whatever is the forecast, it is right. Whatever is the information passed from the parking lot to the operator, that is right. There is no uncertainty in that, it is certain. In that case, you see here that the deviation from target profit. What is target profit? Target profit is the profit that is evaluated based on the forecasted values or the estimated values without any uncertainties. This is certain profit. Okay, so you run the optimal power flow, you run the optimization, you execute the load flow, everything. So you have obtained a network feasible solution in which the aggregator gets this much profit if there is no uncertainty in the given information. That is this one. So there is no deviation from the target profit. The solid line is deviation from the target profit, right? Here. Now, on both sides, you see that there is deviation from the target profit. There is deviation from the target profit because of the uncertainty of state of charge to both sides. The uncertainty can be to the positive side or the negative side. That means 50% SOC was estimated, but in actual case 70 is there. That is a positive uncertainty. In actual case 30 is there. That means a negative uncertainty. So in both cases, you see that there is financial risk inflicted on the aggregator. Why there is a financial risk? Because whenever there is real-time deviation in power, the aggregator will look for reserves or spinning reserves. He has to depend on spinning reserves or grid balance. Grid itself acts as a reserve. So normally, power that is dispatched in emergency requirement, it is costly when compared to the cheaper schedules. The scheduled power will be charged at a different rate and reserve markets will be opened at a different rate. So whenever there are deviations, he has to search for other sources which are costly. So replacing those sources will incur some loss for the aggregator. Thus, it is deviated from the target profit. Already you executed the optimal power flow, you got some result, but it is now deviated from the target profit. Now, what will you do if you have a positive uncertainty? That means more than what is estimated is there, SOC. That means for discharging, enough electric vehicles are available, but for charging, enough sufficient number of electric vehicles may not be available because state of charge is already there. No need of charging, right? So for the scheduled power, it has to go somewhere, especially if it is from renewable energy sources, it is available there. So it has to go somewhere. So either he has to look for load curtailment or he has to look for some energy storage activity. That is negative reserve. So to the negative uncertainty of state of charge, here positive reserve is opened, here negative reserve is opened. For in both cases, the operator incurs a cost, some cost. So based on that, his profit is affected. That is what is happening. So these are the stochastic aspects of scheduling. We will conclude now. EV scheduling shall be ideally smart. What is smart? We have already discussed, right? Automated, information, communication, everything should be properly done, properly sensed. Parameters should be properly sensed from the network. Then economic, it should be either a cost minimized schedule or a profit maximized schedule. Then energy wise risk adjusted, energy balance should be there. Whatever schedule is communicated with the operator, if it is more realistic, then that is more ideal schedule, right? That is energy wise risk adjusted. What is economically risk adjusted? This much profit is estimated from the schedule, but in real time that much profit is not there. There is a diminishment. Then there is a financial risk, right? So the fourth point is financial risk. This is energy risk. Okay, network feasible. When you run the load flow, all the network parameters should be inside the limits, right? It should be within the limits. Then environment friendly. Based on emission cost also, it should not violate the limits. So that's all with this presentation. Thank you very much. If you have any queries, you can ask.